Have you ever felt like there's a kind of magic happening all around us? You know, these invisible pushes and pulls that move the world, but you can't actually see them? Well, today, we're going to pull back the curtain and investigate this unseen world. Okay, check this out. Our first piece of evidence. One magnet is pushing another one away, clear as day. You can see the force, but there's this invisible barrier between them. They aren't even touching. And then there's this classic trick. You run a comb through your hair and suddenly it can just lift paper off a table. Again, it's like a magic trick. No touching, just an invisible pull. And of course, the big one, the one we see every single day. A piece of fruit lets go of a branch and falls. Nothing is physically grabbing it, but down it goes every single time. So what's the connection here? What's going on? This is the big mystery we're going to solve together in this explainer. How is it even possible for objects to push or pull each other across what looks like empty space? To figure this out, we first need to get on the same page about what a force actually is. All right, let's start with the basics. A force is, quite simply, a push or a pull. That's it. It's the thing that makes objects start moving, stop moving, or change direction. Simple enough, right? But that still doesn't explain how it can happen from a distance. Well, it turns out there isn't just one single answer. There are actually a few specific, invisible culprits behind all these mysterious actions. So it's time we unmask them. Meet our lineup. The three main types of non-contact force are magnetic, electrostatic, and gravitational. Some of these are incredibly powerful up close, while another one is actually pretty weak, but its reach is just mind-boggling. Let's tackle them one by one. Okay, let's open up case file number 1, the magnetic force. This is the power we saw at the very beginning with those two magnets playing push and pull. So, with magnets, it all boils down to one simple rule. If you try to push two of the same ends together, like two north poles, they'll push each other apart. That's repulsion. But if you bring opposite ends together, a north and a south, they'll snap together. That's attraction. So the magic isn't in the magnet itself, but in this invisible field of energy it creates all around it. Think of it like an invisible bubble. And it's this field that reaches out across space to push or pull on other magnets that enter its zone. All right, let's move on to our next unseen force, the electrostatic force. This is what's behind that comb and paper trick, and I guarantee you've experienced this if you've ever rubbed a balloon on your head and watched it stick to a wall. Here's how it works, step by step. When you rub two things together, tiny little particles carrying electric charge can literally jump from one object to the other. This creates a buildup of charge, making one object charged, and that charged object now has the power to pull on other things, like those little pieces of paper. Now, this is a really important point. The force here comes from static electricity. Static just means staying still. This isn't the same thing as the electric current flowing through the wires in your wall. This is charge that's just sitting there on a surface, but it's still powerful enough to exert an invisible force. And that brings us to our final and maybe the most famous non-contact force of them all. It's the one that keeps our feet on the ground and, believe it or not, holds the entire cosmos together. Let's talk about gravity. Now, unlike our other forces, gravity is always attractive. It only ever pulls, it never ever pushes. And here's the wild part. It's not just a force coming from the Earth. It's a fundamental pull between any two objects that have mass. That means you have a gravitational pull, your desk has one, everything. We just notice the Earth's because, well, it's just so unbelievably massive. This quote from our source material really hits the nail on the head. That everyday thing we call weight, it isn't really a property of an object itself. Weight is literally the measurement of how hard gravity is pulling on that object. And that brings us to one of the biggest mix-ups in all of science. We use the words mass and weight like they're the same thing all the time, but in physics, they are completely different. It's a true case of mistaken identity. So let's just ask it straight up. Are they the same thing? Well, based on what we just learned, the answer has to be a big, loud no. And understanding why is so important. Here's the difference, and it's actually pretty simple when you break it down. Mass is the amount of stuff an object is made of. We measure it in kilograms, and here's the key. It never, ever changes, no matter where you go in the universe. Weight, on the other hand, is the force of gravity pulling on that stuff. We measure it in newtons, and it totally changes depending on how strong gravity is. This table lays it all out perfectly. Just zero in on that variation row. Mass is constant. Weight varies. That is the single most important thing to remember. Your mass is the exact same on Earth as it would be on the moon, but your weight, oh, it would be dramatically different. And here's the perfect example. An object with a mass of 1 kilogram, well, here on Earth, gravity pulls on it with a force of about 10 newtons. That's its weight. But if you take that exact same object to the moon, where gravity is way weaker, it would only weigh 1.6 newtons. The amount of stuff didn't change at all, just the force pulling on it. And that's exactly why a tool like this, a spring balance, measures weight, not mass. The farther that spring stretches, the stronger the gravitational pull is. It's directly measuring that force. If you took this scale to the moon, it would give you a much, much lower number for the exact same object. Okay, let's do a quick recap. We've unmasked our 3 non-contact forces: magnetic, electrostatic, and gravitational. And we've cracked the case of mistaken identity. Just remember this. Mass is the stuff. Weight is the pull on that stuff. And I'll leave you with this final little puzzle to think about. We know that a tiny little refrigerator magnet can overcome the entire gravitational pull of the Earth to pick up a paperclip. That means gravity is actually the weakest of these forces by far. So, if it's so weak, why is it the one that holds planets, stars, and entire galaxies together? Something to chew on.